The far-off and puzzling universe of Pluto was once viewed as a novel, authentic planet inside our solar system. However, after ongoing discussions by leading astrophysicists Neil deGrasse Tyson and Michio Kaku, Pluto has found itself once again in the spotlight, attracting attention due to their groundbreaking ideas. These experts have suggested that Pluto might be on a potential collision course with Neptune. This thought raises various questions. How might such an event occur, and what could be the consequences of such a great impact? Are we witnessing a fascinating cosmic anomaly, or is there a deeper, more complex phenomenon at play? Join us as we explore the potential ramifications of a Pluto-Neptune collision. Pluto, a former planet once thought to be a smaller and more isolated member of the solar system, continues to be a subject of significant interest and investigation in the scientific community. According to prominent studies by leading experts, Pluto's orbit is dangerously close to Neptune's, and several astrophysicists, including Neil deGrasse Tyson and Michio Kaku, have raised alarms about a potential catastrophic collision between the two. Could such an event pose a significant risk to Earth? How could this happen? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes an extraordinary 248 years to complete just one full orbit. This means that, since its discovery in 1930, Pluto has not yet even completed one whole orbit. However, the intrigue doesn't end there. Pluto's orbit is shaped in an unusually elongated manner, contrasting starkly with the nearly circular orbits of the major planets. What makes Pluto's orbit even more perplexing is its tilt of 17 degrees relative to the ecliptic plane, making it one of the most inclined orbits in the solar system. This inclination, along with its irregular shape, adds to the complexity of its path through space. One of the most fascinating aspects of Pluto's orbit is how it intersects with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying expectations based on their general positions. This raises an obvious question. Why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influence of other planets. The study of Pluto's orbit began shortly after its discovery, with astronomers initially struggling to comprehend its peculiar path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out due to its extreme tilt and erratic shape. The mystery behind the fact that Pluto's orbit crosses Neptune's is rooted in the stability of its path. The key to this stability lies in a phenomenon known as the three-body problem, which deals with understanding how three celestial bodies, such as Pluto, Neptune, and the Sun, interact and influence each other's motion through gravitational forces. This issue is akin to attempting to predict the future positions of these objects based on where they start and how they pull on each other. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity work together in a complex and balanced way. Terms like asymmetric libration, degree libration, and VZK wobbling are part of this intricate issue. According to astrophysicists, what keeps all planets in their orbits is a form of libration. In the case of Pluto and Neptune, this term suggests that whenever Pluto crosses Neptune's orbit, it is always at least 90 degrees away from Neptune's position, preventing a direct collision. Degree libration, on the other hand, refers to the oscillation of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune, it is positioned far above or below Neptune's orbital plane, adding another layer of protection from potential collisions. Another critical factor in this stability is the VZK wobbling, named after the scientists who studied the motion of celestial objects in space. This phenomenon explains how Pluto, Neptune, and the Sun influence each other's movements through their gravitational pull. The wobbling helps us understand why Pluto's path is so irregular. Despite its seemingly erratic movement, the forces at play work to keep Pluto's orbit stable over long periods. These forces are essential in maintaining the stability of Pluto's orbit, preventing it from colliding with Neptune or veering off course. The three-body problem and the dynamics of these gravitational interactions are crucial to understanding how orbits evolve over time and how celestial bodies influence one another. By studying these interactions, we gain insights into Pluto, our solar system, and distant stars and planets. Numerical simulations in the late 1980s revealed that, despite these stabilizing factors, Pluto's orbit can be highly unpredictable, with slight changes in initial conditions leading to significant differences over long periods. However, these irregularities have been shown to maintain a stable orbit over vast timescales. Recent computer simulations have further contributed to our understanding of this intricate cosmic ballet. Recent computer simulations have further shed light on the intricate dynamics of Pluto's orbit. These models confirm that, despite its seemingly precarious proximity to Neptune, the gravitational interplay between the two celestial bodies ensures that a direct collision remains highly unlikely over astronomical timescales. However, the simulations also reveal that minor perturbations, such as the gravitational effects of other planets or passing celestial objects, could introduce subtle variations in Pluto's trajectory. Over millions of years, these changes might lead to shifts in the stability of its orbit. While this is unlikely to result in a catastrophic event, it highlights the delicate balance that governs celestial mechanics in our solar system. The debate over Pluto's status as a planet has only intensified its allure. Originally classified as the ninth planet upon its discovery in 1930, Pluto was reclassified as a dwarf planet in 2006 by the International Astronomical Union (IAU). This decision was based on the discovery of several other similar-sized objects in the Kuiper Belt, a region of icy bodies beyond Neptune. The reclassification sparked controversy among scientists and the public, with some arguing that Pluto's unique characteristics still qualify it as a planet. Regardless of its classification, Pluto continues to be a subject of fascination. Its surface features revealed by the New Horizons spacecraft in 2015 include towering ice mountains, vast plains of frozen nitrogen, and evidence of potential subsurface oceans. These discoveries have challenged previous assumptions about what a small, distant body like Pluto could be capable of and have reignited interest in exploring other Kuiper Belt objects. As we delve deeper into the mysteries of Pluto and its interactions with Neptune, one thing becomes clear: the story of this enigmatic dwarf planet is far from over. Its unusual orbit, complex gravitational relationships, and unique geological features make it a key to unlocking the secrets of our solar system's past and its ongoing evolution. Whether viewed as a planet or a dwarf planet, Pluto remains an essential piece of the cosmic puzzle, reminding us of the vast complexity and wonder of the universe we call home. Researchers grasp how the Goliath planets like Neptune, Jupiter, and Saturn impact Pluto's orbit. For example, Neptune has a unique resonance with Pluto, where for every 2 orbits Pluto completes, Neptune completes 3. This resonance maintains Pluto's orbital stability. However, Neptune isn't the only force at play. Jupiter's gravity also plays a significant role in protecting Pluto's orbit, and Saturn contributes to this stability as well. Simulations suggest that Jupiter's gravity alone is strong enough to ensure that Pluto remains on a stable path for billions of years, possibly even indefinitely. The interaction between Neptune, Jupiter, and Saturn appears crucial in ensuring that Pluto continues to travel safely through space without encountering significant disruptions. These findings are significant in understanding the broader dynamics of the universe. Without these stabilizing forces, the solar system would be a much more turbulent and unstable place. Objects like Pluto could potentially collide with other celestial bodies or be ejected from their orbits, causing a cascade of disturbances throughout the solar system. For Pluto, understanding its orbit is particularly important, considering discussions about a possible future collision with Neptune. This provides a clearer perspective on the dynamic nature of our solar system. The case of Pluto demonstrates how even seemingly unstable orbits can achieve a state of balance through the intricate interactions of gravitational forces and orbital mechanics. It also highlights the importance of continuous research and investigation to better understand our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit serves as a prime example of this unpredictability. The concept of orbital resonance, which refers to the delicate balance of a celestial body's orbit based on its initial conditions, is clearly demonstrated by Pluto. This means that even slight variations in Pluto's position or velocity can significantly alter its long-term orbital path. Computer simulations have been invaluable in studying how Pluto travels through space. These simulations use complex mathematics to model the gravitational interactions between Pluto and other celestial bodies, such as Neptune. By tweaking small details in these models, astronomers can observe how minor changes can lead to dramatic shifts in Pluto's future position. These simulations reveal an intriguing fact about Pluto's orbit. Despite stabilizing factors like asymmetric libration and degree libration, its orbit can still be highly chaotic. Even the smallest changes in Pluto's initial position or speed can cause its orbit to evolve unpredictably over long periods. Yet, despite this chaos, Pluto's orbit remains remarkably stable over billions of years. This suggests that there is an underlying order to Pluto's journey around the Sun, even though it may seem turbulent at first glance. Particularly when considering the complexities of Pluto's highly inclined orbit, The unpredictability of large celestial orbits like Pluto's presents significant challenges for astronomers. The inherent nature of these systems implies that long-term predictions are often fraught with uncertainty. While numerical simulations are excellent tools for understanding and predicting the future behavior of celestial bodies, they also underscore the limitations of our predictions. These models heavily rely on the accuracy of initial conditions and the complexity of the interactions they simulate. A slight error in these conditions can dramatically alter the predicted outcome, making precise forecasts an incredibly difficult task. Moreover, the chaotic nature of large orbits like Pluto's serves as a reminder of the ever-evolving and dynamic nature of the universe. Although we have made significant strides in understanding space, Pluto's example reminds us of how much more there is to learn. Understanding the gravitational effects of the Goliath planets on Pluto's orbit provides valuable insights into the broader dynamics of our solar system. It shows how the positions and movements of individual planets can have far-reaching implications for the stability and trajectory of other objects in the system. But why are prominent astrophysicists now raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces at work to prevent such an event? Neil deGrasse Tyson, a renowned astrophysicist, offers a detailed perspective on the mysteries of our solar system, particularly through the fascinating example of Pluto. Tyson, who played a significant role in reclassifying Pluto from a planet to a dwarf planet, provides a thoughtful analysis of the evolving nature of celestial mechanics and the public's growing interest in the overlooked corners of space. The reclassification of Pluto, Tyson argues, was not a diminishment but rather a necessary adjustment, reflecting our expanding knowledge of the many bodies that orbit our Sun. Tyson's approach to celestial mechanics emphasizes continuous learning and adaptation. He views the complexities of Pluto's orbit and its interactions with Neptune as a reminder of the unpredictability of space. While Tyson acknowledges that Pluto's orbit is stable for now, he suggests it could undergo significant changes in the future. This possibility highlights how much there is still to discover about the forces shaping our nearby solar system. This possibility underscores the intricate and interconnected nature of the solar system. The gravitational dance between celestial bodies like Pluto, Neptune, Jupiter, and Saturn demonstrates the fine balance that governs the orbits and stability of planetary systems. Without these stabilizing influences, the solar system could descend into chaos, with orbits becoming erratic and collisions more likely. Pluto's case exemplifies the importance of orbital mechanics in understanding the broader universe. It also reveals the limitations of our current models and simulations. Despite advancements, the unpredictable nature of gravitational interactions means that long-term predictions about celestial bodies are always subject to revision. Even slight deviations in input data can lead to vastly different outcomes, challenging astronomers to continually refine their understanding. Neil deGrasse Tyson's insights remind us that the reclassification of Pluto was not a demotion but an evolution in our understanding of the cosmos. By defining Pluto as a dwarf planet, scientists recognized the diverse and complex nature of the objects populating the Kuiper Belt and beyond. This decision reflected a broader shift in how we categorize and comprehend the celestial bodies in our solar system. Pluto's orbit serves as a striking example of the balance between order and chaos in the universe. Despite its highly inclined and eccentric orbit, it remains stable over billions of years, a testament to the underlying harmony of gravitational interactions. However, this stability is not guaranteed indefinitely, and future shifts could alter Pluto's trajectory in unexpected ways. The study of Pluto and its interactions with other planets is not just about understanding one celestial body. It provides a window into the fundamental forces shaping our solar system. It highlights how interconnected these forces are and how even small changes can ripple through the vast expanse of space, affecting the stability and dynamics of celestial objects. In conclusion, Pluto's orbit symbolizes the delicate balance of cosmic forces at work in our solar system. It challenges scientists to unravel the complexities of celestial mechanics and reminds us of the boundless mysteries that space holds. As our understanding of the universe continues to evolve, Pluto remains a fascinating case study, illustrating both the predictability and unpredictability of the cosmos. A reminder of how much we have yet to learn about the intricate dance of celestial bodies.